Welcome back to Programming Problems, where today we'll tackle Advent of Code Day 6. During our journey, we get incentivized to partake in a boat race. As we sign up, we discover that we will be racing using a toy boat. We will participate in multiple races, and every race has a time limit and a record distance that we are eager to beat. The race input looks as follows. First, we get a row with the time limits, then a second row with matching distances. The race itself with the following rule. Our boat gains speed via a button at the start of the race. For every unit of time that we hold the button, the boat will gain 1 unit of speed once we let it go. Of course, the longer we hold the button, the less time the boat has to make use of the speed it has. For every race, we can determine the number of ways that we can beat the record. Now, if we take all those ways and multiply them for every race, then what number do we get? Let's take the first race as an example. Let's say we have 7 seconds to travel 9 meters. Then, if we hold the button for 0 seconds, we will not gain any speed. The boat then has 7 seconds to travel at a speed of 0 meters per second, so we're going nowhere fast. Suppose we hold it for 1 second, then our speed equals 1 meter per second. We then let go and have 6 seconds to travel, giving us a total distance of 6 meters. The following 4 options where we hold the button for 2, 3, 4, and 5 seconds give us 4 distances that actually beat the record. Then when holding the button for 6 and 7 seconds, our speed is relatively high, but we have very little time to make use of all that speed. Hence, our total distance traveled goes down again. Given the problem description and this example, do you already see how you can solve today's problem? If you haven't already, consider giving it a go. Let's move on to the solution for part 1. For today's problem, I will show 2 solutions that are both fast enough. The first one is to simply brute force all race outcomes, which exactly what we did for the example. Later in the video, I shall dive into the mathematical solution where we derive a quadratic equation and solve for the roots. For the brute force, the problem outline looks as shown below. We, of course, need to parse our input and get the time values and distances for every race, and then we just solve for every race. The race function is basically a written-out form of what we went over during the example. We'll start with 0 wins. Then, for every possible holding time, we set the speed to the time for which we held the button. Then, we take the remaining time which we have to race, and we multiply them together. If we beat the target distance, then we have another win. For part 2, just as the race is about to start, we realize that the race times which we received just had really weird spacing in them. There is only one race, and we should ignore the spaces between the numbers on each line. For part 2, the problem is the same, but we have a single much larger data point. Let's brush up on our math skills and take a look at the mathematical solution. First up, let's plot the points for the example of part 1. We'll take the time which we hold the button, or our speed, as the x-axis. The distance traveled shall be our y-axis. When we hold for 0 seconds, we travel 0 meters. Holding for 1 second leads to 6 meters. 2 seconds maps to 10 meters, and so on. At the end, the question is, how many of these green points are above our target distance, represented by the blue line? The points themselves are on the green line, which forms the quadratic equation which we are looking for. To work this out, we need to know where the blue and the green lines intersect. To do this, we apply the quadratic formula. But of course, to make this work, we need to figure out what the equation of the green line is, how to get this equation. Well, suppose that x is the time that we hold the button and y is the distance we race. Then the distance can be expressed as the speed times the remaining time, also calculated by the time limit minus the holding time. If we replace with them with simpler variables, then we can see that this is x times t minus x, which itself simplifies to minus x squared plus t times x. And this is already quadratic. Now we win when our distance is larger than the target distance, so we can compare the equation to C. Now back to finding the roots. If we set the equation equal to c, then we can move the c over to the left side to make the entire equation equal 0. And then we have our formula in the perfect form to start finding roots. Finding roots is done via the formula on the bottom, where x is equal to minus b plus or minus the square root of the discriminant. The discriminant is b squared minus 4ac. And then this entire part goes over 2 times a, and we should have 2x coordinates, which is where the lines intersect. Our complete formula thus becomes as shown on the right. Now, there is one final thing that we need to consider before we look at the code. It could be that the distances corresponding to our roots, or x-coordinates, are exactly on the target distance. In these cases, we did not beat the record. We only matched it. The workaround is simple. You can lift the record up ever so slightly. If we ever manage to match this larger record, then by definition, we also beat the smaller record. Making the delta really small guarantees that we won't modify the actual outcome of the problem. My suggestion is to increase the record by 1 nanometer. And finally, last but not least, here is the code to apply the equation that we just discussed. Note that we return right minus left minus 1. The reason why I'll leave up to you as a small exercise. Feel free to comment the rationale below. And that was it once more. We now have 12 stars and we're making good progress. Until next time.